If I divide the year in 12 equal time periods, my return will be higher than this. If I divide it in 365 equal time periods, it will be even higher. This tells us that the dollar at the start of the year will become these many dollars at the end of 1 year. If the number of time periods is 365, so if we increase this number significantly, that is, if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are few more calculations. The number of time periods here is 1 million. Notice that the return improved. Yes, but they converge around a value which is approximately equal to 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding. A 100% growth over one time period. Yes, that's E. Don't forget, we had assumed a 100% growth here, and that's what E is. It's the maximum we get after a 100% continuously compounding growth over one time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2, but after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means that digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely, there is no problem at all. In general, the growth after continuous compounding is given to us as E to the power R times T, where R is the rate and T is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as E to the power 2 times 5. We squared E to include 200% growth and we raised it to 5 as the rough 5 time periods. It will give us E to the power 10. E is nothing but the maximum possible result. Now you're very much clear with this table. It's given in your book. The table shows the value of A0, that is 1 plus 1 over n raised to n as n gets increasingly large. As n approaches to infinity, the approximate value of E to 9 decimal places is approximately equal to 2.718. Here is the graph of an exponential function with base E. You will insert the value of E as 2.718. Insert the input and your function will give some output. Plot the points and join the dots. You'll be getting the graph of an exponential function with base E. Here is the application of base E exponential function. I'll be explaining you the growth and decay application while using this example. It's given in your book. The example is, and this example represents the exponential growth. Cholera, an intestinal disease, is caused by a cholera bacterium that multiplies exponentially by cell division, as given approximately by n equals to n0 e to the power 1.386 times t, where n is the number of bacteria present after t hours, n0 is the number of bacteria present at the start at time equals to 0. If we start with 25 bacteria, how many bacteria will be present in 1 hour, in 3 hours, 4 hours, and interpret. We have to interpret the result after this. Solution for it is, since n0 is the number of bacteria present at the start at t equals to 0, therefore using into the given equation we get, so the value of n0 is 25. We have inserted it here in this formula. Now we'll be solving it for the first part when time equals to 1 after 1 hour. What will be the growth of the bacteria after 1 hour? The bacteria at time t equals to 1 hour is obtained by putting t equals to 1 in above equation. So instead of this time t, you'll be inserting 1. So 99.97 bacteria will be increased after 1 hour. The bacteria at time t. So what will be the ratio of the bacteria after 3 hours? So you'll be inserting instead of t as 3. So 1599 bacteria will be there after 3 hours. Then the third part is the bacteria at t equals to 4. Now what would be the result of the bacteria after 4 hours? The growth will be more. As the time increases, the bacteria will increase as well. So it is 6392. Thus we conclude that the population of bacteria is growing when time t increases. So what we have interpreted, this here is our conclusion. We conclude that as the number of R increases, the bacteria also grows. So that was all about today's lecture.